Rational functions and their graphs. Think back to rational numbers. A rational number is any number that could be written as a fraction. So basically that's what we have here with rational functions is we have fractions. And so here's an example. F of x is this rational function, which is a ratio of two polynomials. Just like with all fractions, we have to worry about a denominator being 0, because if a denominator is 0, it's undefined. So we have to find the domain, and remember we just set this denominator equal to 0, solve, and then we have to throw away those values. So we'll set x cubed minus 2x squared equal to 0. And we'll solve. So we'll take out x squared. Doing a GCF. And that leaves x minus 2. Then we'll set each of these equal to 0. So 0 itself is a bad value, and this one, when we solve, x equal 2 is a bad value. This says to write our domain. Now, domain is what you do have, so we start out with the set of all real numbers, and they are asking for set builder notation. So x such that x is an element of the reals, x is not equal to 0 or 2. Let's find the domain of the following rational functions. So we look at the denominator and we will set it equal to 0 and solve. This one is a difference of squares. 11 times 11 gives us 121. So we have x plus 11 and x minus 11. Equals 0. So negative 11 is bad and positive 11 is bad. And so our domain, we'll call it D, is the set of all reals. So x such that x is an element of the reals and x is not equal to negative 11 and positive 11. The next one is a little tricky. So you would start the same way, and you would set x squared plus 5 equal to 0. And you would want to solve that. Well, this doesn't factor, so if we try to solve it a different way, we could subtract the 5 from both sides and use the square root method. So x equals plus or minus square root of negative 5. But this is a complex number. So this is plus or minus 5i, and those are not real numbers to throw away. So your domain here is going to be all reals on this one because we did not get a real number that would make this denominator 0. So our domain here is negative infinity to positive infinity. Next, we have some terminology that we need. First of all, asymptote. An asymptote is a line that the graph approaches. It never actually touches, but it gets close as either x or y values get extremely large. And I have called this before that it blows up there. Right? We show them on our graphs with dotted lines. It's not a real line, but it's like an invisible line that you're going toward. So if our function is a rational function in which p of x and q of x have no common factors, so they have nothing you can divide out, and if a is a 0 of q of x, all right, so in our domain that's something we would throw away, then x equals a is a vertical asymptote. So these pieces that are zeros of the denominator that we would throw out of the domain, that's where the graph is going to blow up. So these will be our vertical asymptotes, and they will be of the form x equals a. So to find the vertical asymptote, set the denominator equal to 0 and solve. They are vertical lines, so they will be of the form x equals your constant, whatever it is here. Our next question asks, what is the relationship between the domain and the vertical asymptotes? Well, the things that you're throwing out of the domain are actually what makes the vertical asymptotes. So for this problem, we set x minus 3 equal to 0. And so x equals 3. For the domain, we're going to say this is the set of all reals, and x is not equal to 3. For our vertical asymptote, we set our denominator equal to 0, and this is actually our vertical asymptote, right? This piece that we throw out of the domain. And so on the graph, let's see if I can do this without making too big of a mess. Here is x equals 3, and notice as you get farther down this way, it's going to get closer and closer, but it blows up here at the 3. It can't get down to the 3. It goes away from it. Here it's going to go toward this, and this way it's going to go toward. So that's toward the vertical asymptote. This one has another asymptote, but we'll just deal with the vertical asymptote right now. Right, this problem is one from our software, and it asks us to find the vertical asymptotes, if any, and the values of x corresponding to holes. We'll talk about holes in a little bit, so now we're just going to say there are no holes. But all we have to do is set this denominator equal to 0. Solve, so add your 6. And that is a vertical asymptote. And so our choice on here is going to be A. The vertical asymptote is x equals 6. And there are no holes. Here we have another example. I just wrote our function bigger, and they want us to find the domain. So we set the denominator equal to 0. I'm just going to move this way a little bit. Factor, this is a difference of squares. And so x equals negative 2 and x equals positive 2. Those are bad values. So when you're answering domain, you're going to throw those away. So the domain is the set of all x such that x is an element of the reals and x is not equal to negative 2 and positive 2. The other part asks us for the vertical asymptotes, and that is these pieces we were throwing away. So x equals negative 2 and x equals positive 2. And I'm going to try to draw them on this graph. These lines don't really touch them. They just get closer and closer. So this is it, but it's not really touching it. That's x equals positive 2. And this is x equals negative 2. The graphs go toward them. And we still don't have holes. So let's look at what are holes. We've mentioned them a time or two. If you have common factors between your numerator and your denominator, and you do here, if you factor your denominator, you have x plus 2, x minus 2. And so this x plus 2 would divide out. But this piece that divided off the denominator, we're going to get a whole from that. So x plus 2, we want to know when that is 0, and it is 0 at x equals negative 2. This will give us a whole. The other one would give us a vertical asymptote. So x equals 2 is a vertical asymptote. So when it has a common factor with the numerator and denominator, the piece that would divide off the denominator, set it equal to 0 and solve, and that would give you a whole instead of a vertical asymptote. If you want to know where this whole is at x equals negative 2, plug that into your piece that's left, and so it would be 1 over negative 4. So at negative 2, negative 1/4 is the location of this whole, or this open circle in your graph. So if you graphed this first piece, if you graphed this, right, you would get a whole at this spot. It would be an open circle in the graph at negative 2, because negative 2 is an excluded value. If you did this one, which is what you get after it's reduced, you would not get a whole. We have one more thing that we're going to define, and that is a horizontal asymptote. And the horizontal asymptotes are going to be of the form y equals some constant. Horizontal asymptotes may be crossed, right? And we work with this little table to decide what the horizontal asymptotes are. So it depends on our degrees of our numerator and denominator. So our first situation, if the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is y equals 0, or the x-axis. Right? Case number 2, if the degree of the numerator is equal to the degree of the denominator, your y is equal to the leading coefficient of the numerator over the leading coefficient of the denominator. And the third case, if the degree of the numerator is bigger than the degree of the denominator, there is not a horizontal asymptote. So we have 3 rational functions here that we want to find the horizontal asymptote. And so we're going to refer back to our little table. And so we're looking at the degrees of the numerator and denominator. The degree of the numerator on this one is 1. The degree of the denominator is 2. So the degree of the numerator is less than the degree of the denominator. This is our first case. So y equals 0 is our horizontal asymptote. This one, degree of the numerator is 2. Degree of the denominator is 2. So they are equal. That's case number 2. Your y is equal to the leading coefficient of the numerator over the leading coefficient of the denominator, and this will simplify to 2. So y equals 2 is a horizontal asymptote. Our third one, degree of your numerator is 3. The degree of the denominator is 2. So this is our third case where your degree of the numerator is bigger. There is not a horizontal asymptote. I want to just go through this strategy quickly for graphing a rational function to kind of pull all these pieces we've looked at together. So the following strategy can be used to graph this rational function. And this one states that P and Q have no common factors. So you're not going to get holes if these have no common factors. But so our first step in the strategy is to look at symmetry, right? And do it algebraically. Plug negative x into your x. If you get back the original when you do that, you have y-axis symmetry. If you plug negative x into x and you get back the opposite, so you only have to plug the negative x in once. If you get back the original, you have y-axis symmetry. If you get back exactly the opposite, you have origin symmetry. You do not have to get either one. Right? Step 2 is find the y-intercept. Remember, y-intercept is set x equal to 0. So you're going to plug 0 through and solve. There doesn't have to be 1. Right? Find the x-intercepts if there are any by setting your function equal to 0. And when you set your function equal to 0, so if my f of x is 0, only the numerator has to be 0, because 0 over anything gives you 0. So I just set 0 equal to the numerator to get x-intercepts, if there are any. Right? Find your vertical asymptotes. Remember, this is looking at your denominator and seeing what makes it undefined. But you're going to have those as vertical lines. Right? So it would be, you would throw them away if it was domain you were doing, but you were just, when you set them equal to 0 and solve, you're going to get vertical lines. So x equals some constant. That is your vertical asymptotes. Your horizontal asymptotes, if there is one, we're going to use that little table we just looked at. Right? You're going to plot at least one point between and beyond each x-intercept and vertical asymptote. So these asymptotes and intercepts are going to divide your grid into sections, and you need some points in each section to tell how the graph acts. Use the information obtained previously to graph the function between and beyond the vertical asymptotes.